Hello. I hope you guys are doing well in these crazy times that we're living in. I'm down here in the basement of Magruder Hall, and it's really lonely around here. We're missing you guys. So I hope you're all staying healthy and keeping your brains working. We're talking today still about the RC filter circuit. So we're talking about an RC series AC circuit. And in any series circuit, the voltage divides, but in an RC series circuit, the way the voltage divides depends on the frequencies. For low frequency source, for a low frequency circuit, all the voltage appears across the capacitor, and for a high frequency source, all the voltage appears across the resistor. And this circuit is useful in that it can divide up a mixed circuit that has both high and low frequencies. It can break up the high from the low frequencies. The transition point between what we mean by low and high frequencies is something called the break frequency. And the angular break frequency is just the inverse of the product of the resistance and capacitance. You might remember that the product of RC is a time. So 1 over that time is the break angular frequency, and the break frequency and the break angular frequency are related by 2 pi. Omega equals 2 pi f, you probably remember. Your lab write-up works through all that theory, and it's important that you go through that theory and ask questions about things you don't understand. When we excite such a circuit with a sinusoidal input voltage across the combination of R and C, the output, which appears either across R or across C, always has the same frequency as the source. So the question is about what happens to its amplitude and what happens to its phase relative to the source's phase. The fact that it's a linear system is why the frequency of the signal out is equal to the frequency of the signal in. So the question's about amplitude and phase. And so we measure the ratio of the output voltage to the input voltage. That's called the gain. And we already did that last week, and I sent you that data for analysis. So today, what's left to do is to study the phase relationship. How much is the phase of the output signal shifted relative to the phase of the input signal? So that's what I want to show you, how we measure that today, and then I'll send you some data regarding that. So I'm going to move to the other table where there's some equipment set up. Here we go. Okay, so here we are over at the lab bench, and we're back to, here's our capacitor, and here's our resistor. And right now they're configured in the high-pass filter configuration, although that's not that important. Here's our resistor and our capacitor. Way over here we still have the capacitance meter and the ohm meter, the multimeter that we use to measure the values of the resistance and capacitor. I demonstrated that last time. Over here we have our signal generator. I can adjust the frequency, and on top of that I have a frequency counter. And notice they're connected together. The sync output of the signal generator is connected to the frequency counter. And now what's different is, instead of having 2 voltmeters, 2 multimeters, we now have an oscilloscope. And an oscilloscope is nothing more than a voltmeter with a graphic output, so you could look at the shape of AC signals. With a multimeter, all you can do is get an average of those time-varying signals. With a scope, you can actually see them. And so what I have here is channel 1, which is this one here, is hooked up to, back over here to this orange one, to the source. So that's channel 1. And channel 2 is this blue wire. Over here is channel 2. And that comes and looks at the signal across the resistor. So the output is across the resistor. The input is across the combination. And now let's look at what we see here. Channel 1, remember, is the source. So it's the one that's moving up and down. That one. See if I can back up a little bit. That's what's the input to the circuit, and the output, what's across the resistor, that's this guy that I'm moving up and down now. Of course, they look like they're the same height, but they're set on different scales. Remember, this is a filter, and so the high frequencies will be big and low frequencies will be small, but that's not what I care about. So I'm going to adjust these two scale settings, making the image bigger or smaller, so the two signals are roughly the same height. Roughly the same height. I can also adjust the time scale. So this is really a graph of time versus voltage, and I can adjust the time scale. So the goal that I'm after here is to measure essentially the time difference, but can't see that, let me put the camera better. The difference between the two peaks. And so the way to do that is to, number one, make that as big as possible by opening up the scale. So now I'm going to measure the distance, the time from the lowest peak to the lowest of the other peak. And the way I'm doing that is I'm going to position these. I got position knobs over here that I can move things around. I'm going to put the peak on the central axis, and then I'm going to do that with the other one as well. Whoops, that's the same one. And then I'm going to very carefully measure the number of divisions from the minimum of that curve to the minimum of that curve. And I'm also going to write down the scale setting here. This tells you how many seconds or microseconds or milliseconds per division. So this number plus this measurement over here multiplied together gives us the time lag between these two signals. And that multiplied by the angular frequency gives you the radians, the number of radians of phase shift. And so we're going to measure that. We're going to adjust the frequency over here and then go back and measure the phase shift, frequency as a function of phase. So I've done that, and here's my data. Over here, this is what the data looks like for the low-pass filter. I've labeled my R and my C. I've drawn the circuit. The output across the capacitor is the low-pass filter. Here are the frequencies that I measured from the frequency counter. And then here's the time per division setting, and here's the number of divisions right here. If you multiply these two columns together, you get a time lag, and if you multiply that by 2 pi f, then you get a phase shift in radians. And so that's what you're trying to calculate and plot graphs of. So I guess that's pretty much it. That's kind of what the situation looks like. That's what you would have done had you been here. Set up the circuit, measure the capacitance and resistance. By the way, on the low-pass filter, I did the same thing I did with the amplitude data. The low-pass filter has a different resistor and therefore a different break frequency than the high-pass filter. And they're labeled on the data sheets. Okay, I'm going to sign off now.